But fortunately, I keep it so clean that there's never anything like that. So it's great. So we were drinking from the fire hose last time. We were doing this example, and I had actually, I think, refrained from using that phrase, but I did not this time, unfortunately. So fire hose, we've got this nice tank of water that has a pump. It's pumping it up, the pressure up, and water is flowing out the fire hose to atmospheric pressure. We drew the linear graph and normal tree, and we would like to know what the transfer function is from the pump pressure to the velocity of the spray. I didn't have this before. So if we have the velocity of the water coming out, and that's what we want our transfer function to be too, then we probably should try to express that in terms of a flow rate, which volumetric flow rate, which one specifically? I would say the closest to it would be R, the resistance, so Q sub R. That's in SI units, meters cubed per second. If we would like to turn a volumetric flow rate into a velocity, we have to divide by the cross-sectional area, which the cross-sectional area of the nozzle is given as A in the problem. So what we're really looking for here is QR. Well, what we're really looking for at the end of the day is what is the output V divided by the input PS. What is that in the Laplace domain? What is that transfer function? So that's our goal, is to analyze this problem and find that relationship. We know that we're really searching for QR, though, in terms of the variables that we're going to write down for our fluid system. So that's our main kind of direction, our trajectory here. So let's do 1B, which I'm going by this list here. We drew the normal tree. We're now going to write a Laplace domain elemental equation for each passive element. And elemental equations for each passive element here. So we have C, L, and R are going to be that the across variable PC is going to be equal to QC, the through variable, times the impedance ZC. And for the fluid inertance or fluid inductance, L, we're going to have a similar equation. I'm going to, well, we'll just write it the same way, just so you get the idea here. PL equals QL ZL. And then finally, PR equals QR ZR. So all the elemental equations are this like generalized Ohm's law sort of situation, right? Generalized Ohm's law. Generalized squared Ohm's law. Yeah. And we do have a habit of doing this, and it is still useful to do when we use this method, solving each of these for the secondary variables. The ones that show up in the normal tree, the branches, C and R, they are both already solved for the primary variable here, because the cross variable is primary in the normal tree. And so we've got to solve for the primary variable for the link, so QL equals PL over ZL. This isn't required, strictly speaking, but it's useful. And then let's say let's write down each of these impedances. ZC equals 1 over CS, ZL equals LS, and ZR equals R. Now, I recommend not plugging in those impedance values until the very last step. Otherwise, you're just going to carry around a bunch of S's. There's really no need for it. So just leave everything as ZC, ZL, and ZR. Do your solution, and then at the very end, plug in those values of S, or values for Z, and then simplify it down at that point. Save you a lot of headaches along the way. So now we are on step 1C, which is the continuity equations. Now, I didn't write them, but PC, QC, etc., they're all functions of S, right? I'm suppressing that just because it just looks really messy, and it's easy to actually introduce errors if you write down a bunch of pointless function of S terms in there. I think that we end up making more mistakes that way. That's why I suppress it a lot of times. So we just have to know from context, okay, these are functions of S because we used an impedance equation, which has to be in terms of functions of S. Okay, continuity equations. We need to write one for each passive branch, so each passive branch in the normal tree. I already drew these contours for the earlier section. What do you guys think? Should we use them? We should use them. So this one was the contour I drew for R. So that contour works for R because it only intersects one branch, and it's just that branch. And so we are able to read off that the through variable QR is equal to the through variable QL going into the contour. So QR equals QL. And we could draw this contour for the C element, which gives us that QC is equal to negative QL. QC equals negative QL. All right, compatibility. How many compatibility? There's like a lot of I's in there. How many compatibility equations do we have? One. Corresponding to which element? L. So we find out that PL is equal to PS plus PC minus PR, right? So PL going around the loop from tail to head of L, PL equals PS plus PC minus PR. Very good. So we're done with step 1. Now we're on step 2. And I'm actually going to add in a 2A. I didn't list a 2A in the lecture, but we have this really nice ability to eliminate all the secondary variables in one swoop. So let's just do that. So let's just eliminate secondary variables. What we're doing in this step 2 is we're solving this. We have 6 equations, 3 elemental equations, 2 continuity equations, and 1 compatibility equation, and 6 unknowns. The pressure and flow rate for each of the passive elements in the graph. So we're really just solving a linear algebraic set of 6 equations and 6 unknowns for the 6 unknowns. We only really care about QR, though. So maybe we won't have to go through the whole process of solving out everything. But this first step, we know that QR equals QL, but that doesn't help us. So let's go ahead and eliminate secondary variables. Unfortunately, kind of, QR is a secondary variable, so we're going to eliminate it. But fortunately, QL is a primary variable, so we're not going to eliminate QL, and we know that those two are equal to each other. This always works this way. So if you want to know a variable that is a secondary variable, and you eliminated it this first step, no big deal. Solve for the primary variables that it's equal to from your continuity or compatibility equation, whichever one it's coming from. And then you've got it by just using that equation. So all we need to do is solve for QL, and we know what QR is. It always works that way. So eliminate secondary variables. So we can rewrite our table, our CLR, and we can, we had PC equals, so ZC, and then QC is what it used to be, but now we have a continuity equation saying that QC equals negative QL, so we'll put a negative in there. I should have given myself a little space. Negative ZC QL, and L is the continuity equation was QL equals 1 over ZL times, it was PL, now it's going to be PS plus PC minus PR. And finally we had PC equals Z, or not PC, PR. PR equals ZR times, it was QR, but now we're going to plug in QL. We already used this in the last step. So QL. Now, in a minute, we're going to recognize that this middle equation has QL in it, PS in it. We have a solution for QL, except that we have PC and PR we need to get rid of. But the C equation and the R equation, both substituting those into this equation for PC and PR, eliminate those variables, and we are left with just QL and PS, which is an input, so we can solve for it. We can solve for QL. But so I want to, before we do, so we could do that. We could do that. We're going to do that. But I want to show you what would happen if we looked at this and we were like, okay, this is a system of equations. I don't see how to get to the solution I want right away. How would you do it in general is the question. And you guys have been solving linear equations for so long, it almost feels like, oh God, like, are we going to do this again? But let's write it out just once, just to see what it would look like. And I'm not even going to go through the whole process. But so I'll say 2b, solve for, see, what did I called? Yeah. So solve for I guess it would be QR. So this is, I would say 2b1 is the long way. This is the general way that you would do it. You would form a nice linear algebraic system. You would need to use a 3x3 matrix here, and that would be multiplying your unknown variables P, C, Q, L, and PR. And it would be equal to whatever is on the other side, whatever is not multiplying one of those variables, which in this case is going to be anything multiplying PS. If you wanted to be fancy, you could do this, knowing that that's what's going to be over there. So, and if there were more, you could have either more of these added together, or you could have a matrix multiplier as well with multiple inputs. Up to you. But let's fill this in. What you do is you just transcribe these equations into this matrix form. Okay. So the first equation, we're going to move everything to the left-hand side, okay? So I'll do it first here, and then I'll transcribe it. So we'll have PC plus ZCQL equals 0. So we'll have 1 PC and plus ZCQL plus 0 PR equals 0. That's that one. The next equation, let's move everything to the left-hand side here. So we have QL plus 1 over ZL PR minus 1 over ZL PC. Getting a little fast and loose with my L's and C's. That's very dangerous. And finally, I'll leave the term on the right-hand side with the input. So 1 over ZL PS. So transcribing this, I have negative 1 over ZL PC from this term. 1 QL from this term. And 1 over ZL from this term equals 1 over ZL PS from this term. And finally, this last equation is very similar to the first equation. We have PR minus ZRQL equals 0. So we have 0, we have negative ZRQL, and then we have 1 PR equals 0 PS. Let's name these so we don't have to write it. So I'm going to call this the gamma matrix. I'm going to call this vector little m. Yeah, little m is okay. I'll use it. And I'll call this it's like so few letters we can use. Z. Call it Z. Yeah.
Why don't you use the naming convention from mechatronics books?
So the naming convention for mechatronics, I'm not doing that because this is not the state vector. So this isn't the state vector. This is not like the A matrix or the B matrix or anything. So that's why I want to I want to stay away from those symbols because they're not those things. They just look a little bit like it. Yeah, exactly. So what we want is the solution for M. We want PC, QL, and PR. So M is just equal to gamma inverse times Z. So you just take the inverse of this, left multiply both sides, and you've got yourself M, your solution. That is just the general way to do this. It's, fine. You can do it that way. There's in this case we can go with the 2B2 way, which is to say substitute and find QL. That's the only one we care about. So we don't really care if we get a solution for PC and PR, because the question didn't ask for anything that was related to that. We only care about what QL is because we care about what QR is, because we care about what V is. But that's the specific question that was asked. We could care about something different, and that would change what we're solving for here. So QL is pretty easy to find by just saying, oh, well, it's just from this equation, it's given. Just plug in PC and PR. And in fact, we could use this form of the equation because PR is going to be a function of QL, and PC is going to be a function of QL. So we're going to end up with a bunch of QLs on the left-hand side. So let's just do that. So we have QL plus 1 over ZL times PR, right? But PR is just going to be ZRQL. Plus, or minus 1 over ZL times PC, but PC is negative ZCQL. So the negative becomes a plus, and we're going to have ZCQL equals, on the right-hand side of that equation was a 1 over ZL PS. Very good. We can factor out. One thing we can do to simplify this thing immediately is to factor out QL on the left-hand side and also multiply both sides by ZL, right? Because there's a lot of over ZLs happening here. So let's do that. And if we factor that out, then what we're going to get is ZL plus ZR plus ZC times QL equals PS. And if we're interested in the transfer function from PS to QL, which we are, we're interested in that transfer function, which we're going to turn into a transfer function from PS to QR, which we're going to turn into a transfer function from PS to V. Okay, so that's the transfer function we want. It's the output over the input, so it's going to be, therefore, the output QL over the input PS is equal to 1 over ZL plus ZR plus ZC. Very good. Now, if we had, so step 3, we just did step 3 actually. So this is step 3. We solved for this ratio. Now, if we had another input, say there was another input on this side, so like we had some other term and it was like a flow source that was also in here. If we wanted to know this transfer function from PS to QL, we would have to set this to 0 temporarily to find that. We didn't have to because there wasn't one. And if you wanted to know the transfer function from QS to QL in this made-up part of the problem, you would have to eliminate that term, and that's what step 3 is all about. Is showing you how to do that, or telling you how to do that in general. Now, okay, so we ended up with this transfer function. That's great, but what we need is the transfer function. What we want is so say 4. We want V over PS, which is equal to, we said that V is QR over A, so Q.
Is it QR or just Q?
Well, we haven't defined something called Q, so we had to choose some flow rate, some element. I chose R. We could have also said QL. It's the same. All of these flows are the same, except there's a negative sign on these earlier ones. But that's, yeah. on C. If we had done for QC, we would have had to take a negative sign on it. But yeah, this is one loop, so they all have the same through variable. And QR is just QL, so we have QL over APS. And this from right here, so we can just substitute that in, is the fraction 1 over A in the numerator, ZL plus ZR plus ZC. At this point, we should probably plug in ZL, ZR, and ZC. So I'm going to move the 1 over A out here. Times 1 over LS plus 1 over CS plus, ZR was R, and ZC was 1 over CS. An easy way to simplify this is to multiply numerator and denominator by CS, which leaves us with 1 over A times CS in the numerator, LCS squared, plus I'm going to switch the terms. No, I won't switch terms. RCS plus 1, which writes them in descending order of S polynomial, simplified fraction there. And that is our transfer function. That's our answer. Cool beans?
So how would we go from this to actually knowing the velocity?
Yeah, so depends on the method you want to use. So right now we haven't learned how to find the well, I would say if you wanted to know the forced response, which is not the goal of why we found the transfer function in this case, but say you wanted to, you would just say that your V of t is equal to so I'll back up for just a second. V of s over ps of s equals, I'm going to call this something. I'm going to call this h of s, the transfer function, h of s. And that implies that v of s equals h of s times ps of s. If you wanted to know the forced response, you could take the inverse Laplace transform of both sides, which would give you v of t on the left-hand side, and would give you the inverse Laplace transform of h of s ps of s. And that's your forced response. That would be the answer. That inverse Laplace transform might suck, but it would be the solution. So, and you can't solve it until you know what PS is, right? So that's the input, that's the forcing function. It's hard to know what the forced response is until you know what the forcing function is. So
if it was a constant pump.
So that would be like a unit step, which has a Laplace transform of 1 over s. Is that right? I should know this. I think it's 1 over s. I'm pretty sure. Something like that. It's close to it. I think it's 1 over s. And so if you take 1 over s, multiply it Then you would have this S would cancel with that S, and you would take the inverse Laplace transform of this. You would need to know what your R, C, and L are to know if this is going to, you need to find where your roots are and all that. But yeah, I mean, it's second order. That's in a table. You could look that up. Yeah, so the inverse Laplace transform, just the way that you've done it in previous classes, is what you would use to do it. It's pretty fun, but that's not, so that is a method for finding the forced response. That's not the method that we're going to focus on. I mean, that's, if we want to find that, we already know how to solve the input-output ODEs. So we could transform it into that form. We already know how to solve the state equation, so we could solve it in that form. We could also solve it using the transfer function, but like, that's like the one solution method that I don't go into in the class, just because it's just a lot of work, and it's not necessarily, I mean, you guys have technically seen it before. It's good to know that this is true, but going through it again in detail isn't what we're going to do. But yeah, it's a good question though.
Because it looks like the problem's for fluids. I was wondering if we knew the same things from fluids. One, if we would get the same answer, and two would be like how much more work where we solved is it to get to the answer.
Yeah, I mean, it depends on how you're modeling it in fluids class. Yeah. I'd be interested to see the problem that you're talking about, like a fluids problem that you're discussing, because it could, I mean, you could potentially have this solution depending on the model that you're using in fluids. But yeah, and I mean, at the end of the day, all of these are dynamic models, which means they're all differential equations underlying them. At least that's the model that we're going to use for all of them, even if it's a continuous model, like in the fluids class, or at least at some point you're going to have these continuous models where each point in space has a different velocity. Each particle in the fluid has a different potential of like velocity and pressure associated with it. Whereas for us, it's like, everything in the hose along this cross section is at the same velocity, which is just a fiction that is useful. But we just say, it's the average velocity along that profile. That's what we're solving for. Yeah. So yeah, I mean, you guys could be doing the same sort of analysis. I mean, it's realistically, a lot of these methods, if you make the right assumptions, they end up being equivalent to each other. So, yeah. Cool. All right. Good. Let's call that good for this lecture.